let's assume we have this block of radioactive material, and let's also assume that we know the half-life of the radioactive block, and let's arbitrarily choose that to be 5 seconds. Of course, I just chose that arbitrarily. It could be 10 seconds, it could be 50 seconds, it could be 100 years. So I just chose it to be 5 seconds. And what this actually means is that after time t equal to 5 seconds, this radioactive block would have reduced to the half of its initial amount. So this would have broken into half. See, so half of it would have decayed at a given amount of time. Half of this would have decayed, right? So half of this would have decayed. So after time t equal to 5 seconds, the radioactive block reduces to half of its initial amount, right? So 50% of this would have decayed. 50% of this would have decayed. So let's also assume that at time t equal to 0 seconds, at time t equal to 0 seconds, which is actually at the time we still have 100% of the block, and let's assume that at this time t equal to 0, we have this supernatural power to pause time and zoom into see the section, and zoom in actually to see the particular section of this block, right? And look at the individual atoms that make up these particular sections. So let's draw that out. So let's assume that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have 18 atoms. Of course, we are actually simplifying this. So we might have billions and thousands of atoms which make up this section. We are assuming that it's actually 18 atoms, right? Okay, so since we are given the half-life to be 5 seconds, and if we actually know the number of atoms or the amount of this radioactive material, what we don't know is that we could actually tell the number of atom. So the number of atom or the amount of atom that will decay for a given period of time, right? Because we are given the word the half-life and the amount of the radioactive block. So if we are given these values, we can say that this is the amount of this that will decay at particular time t, right? So, and also we can also tell the percentage that we decay for a particular time, given the half-life and the amount that you start with, right? So, but what we don't actually know is that we can't tell which of these atoms will decay at a particular instant of time. So we can't tell that, oh, this will actually decay now, this is going to decay now, this is going to decay now, this is going to decay now. So that is not possible, because all these atoms have equal chances of decaying. So what I want to drive here is that the process of radioactivity deals with probability, or it's actually probabilistic in nature, right? So we can actually say that, okay, that probably this is going to decay now, probably this is going to decay at time t equal to 5 seconds, probably this is going to decay at time t equal to 3 seconds. So we can only talk about this in terms of probabilities, right? Well, what we do know is that we could actually tell the amount that we decay at a particular time, right? Okay, so we can actually tell which or the amount or the percentage that will decay at a particular time. All right, so and also let's actually see, because now if we are given this amount of radioactive material after time t equal to 5 seconds, this will reduce to half of its initial value. So since we have 18, it's going to reduce to 9, right? So this is going to break in half. Now this might not actually break in half, because since radioactivity is a random process, it might actually be that this will decay, this probably this will decay, probably this will decay, probably this will decay, probably this will decay, right? And probably this might decay, right? So at time t equal to 5 seconds, 9 of these atoms would have decayed, right? So we have 1, 2, 3, 4, 5, 6. So probably this would have decayed, this, right? 1, 2, 3, 4, 5, 6, 7, 8. This will have decayed after time t equal to 5 seconds. Of course, this deals with probability. It doesn't deal with absolute precision. And so after time t equal to 5 seconds, this would have reduced into half of its initial value, right? Okay, so let's try to look at this quantitatively. Let's clean this up a bit. Let's change color. Okay, so let's say we have this amount of block of ice. So let's start with this amount of block of ice, and also that is for the first experiment. Now for the second, let's start with this amount of block of ice. Of course, we are assuming that we have the same radioactive material, And let's assume we have this amount of block of ice. Of course, we do know that if we know the amount and the half-life of this block of ice, we can actually tell the percentage that will decay at a particular time, right? Okay, so let's assume that 30% or 50% of this atom will decay at time t equal to 6 seconds. Of course, I'm choosing that arbitrarily. 50% of this will decay after time 6 seconds. Of course, since it is 50%, of course that should be an half-life, right? So t should be an half-life. Okay, so after time t equal to 6 seconds, this will reduce to half. So it will break in half. All right, so we just have this and this, so this would have decayed. All right, okay, so of course we are actually depicting the amount using the area of this block. All right, so we have this block remaining. That's for the first experiment. Now for the second, all right, of course we still have the same material, the same radioactive material. So after time t 6 seconds, 50% of this would have also decayed. So I'm trying to depict this to be the same, to make sure that we still have the same area with this. All right, so half of this would have also decayed, so we just have this left, right? Same thing here, so half of this would have decayed, right? So we just have this left, right? Now, if you should look at this, the amount that will decay, right? This is actually becoming messy. Let's clean some space. So the amount that will decay, at a particular instant of time depends on the amount that we have. So if you start up with something small, of course the amount that will decay for a given amount of time will be very, very small, right? If you start up with something big, the amount that will decay at a given amount of time will be big, right? So we actually want to care about the instantaneous amount that will decay, right? The instantaneous amount that will decay. So we want the amount that will decay every seconds, right? Every seconds. And that is actually denoted with dn dt, right? dn dt, where n is the amount, the amount, right? N is the amount, so dn dt. Of course, in the next few minutes, what we're going to do is going to be maths intensive, all right? So, and it's going to we're going to derive some formula using calculus. So if you don't like calculus, just skip the video, or you could forward the video to see the final equation that we're going to derive, right? Okay. All right. So we mentioned that that the amount that will decay, which is dn over dt, at a particular time. So the instantaneous amount that will decay depends on the amount that we start up with, right? So it is directly proportional to the amount that we start up with, right? Now, since it is decaying, so the number is actually reducing, so we put a minus sign there, right? Okay, so the negative dn over dt is directly proportional to the amount that we start up with, or the amount that is remaining, right? Okay, so of course we know that mathematically we could remove this proportionality sign and put an equal sign. So we have dn over dt to be equal to, so we put in a constant, then we have n, right? So we put a constant there and we have n. So let's try to see what this constant actually is. So we have n equal to, lambda equal to negative n 1 over n, negative 1 over n over dn dt. So what we did here is just actually dividing both sides by n, right? Both sides by n. So this cancels out, right? So we have this. So of course, what this actually means is that because this dn over dt here is actually the number that will disintegrate per seconds, right? So number let me use that for number that will disintegrate per seconds, then that's all over the number present at that instant, right? Number present at that instant, right? So number that will decay per seconds over the number that is present at that instant of time. Now the unit of lambda is per seconds, right? Because the number here, we cancel the number here, so we just have time, so we have per seconds. All right. Okay, so this constant is actually called the decay constant. Decay constant. All right, so of course, if you should look at this equation, let me clear some space. So if you look at this equation, of course this is a differential equation, right? A separable differential equation. So let's separate the variables. So we have the n, so let's divide both sides by n. So we have the n over n and multiply both sides by dt, right? Because we want to separate the variables so that we have one variable in one side of the equal sign and the other variable in the other side of the equal sign. So we have minus dn over n. We have lambda over the lambda times dt, right? Okay. Now, since we have a differential equation, now we want to integrate this. So we need to integrate this from time t equal to 0 to time t equal to t, right? T seconds. 0 seconds, t seconds. And we know that at time t equal to t seconds, that is when we have n to be the initial amount, right? The amount that you start up with. And at time t equal to t seconds, which is the amount that would have passed, and that is going to be the amount that will remain at that time t seconds, right? So we want to integrate this. So we have integral from n0 to nt, from n0 to nt of negative dn over n equal to the integral from 0, right? From 0 to t, from 0 to t of lambda dt. Okay. All right. So we can take this minus sign out of the integral sign. So we have negative integral of n0 to nt of dn over n equal to, and we could also take this, because this is a constant, so we can take this constant out of the integral sign. So we have from 0 to t of the t. Now in calculus, when you have the integral of with respect to t or n or any variable divided by that variable, right, it will be actually equal to the natural logarithm of that variable plus c, right? Okay. So here we have n, so it's going to be the natural logarithm of n. So we have negative natural logarithm of n from n0 to nt equal to lambda. Now this is going to be t if you should integrate, just because we have just one here. So if you should integrate one, we just have t from 0 to t, right? So this is just going to be, so we could actually multiply both sides by minus. So we have minus here, right? Okay. So we have natural logarithm of n from n0 to nt, then minus lambda t from 0 to t. So this is going to be, so if we evaluate this, is going to be n, the natural logarithm of minus the natural logarithm of n naught equal to negative lambda, then t minus 0, right? T minus 0. Of course, if you don't like calculus, just keep to see the final equation. All right. So using the logarithmic property, of course, the natural logarithm is actually the logarithm to the base of e, right? The logarithm to the base of e. Now in mathematics, e is actually a number, right? So it is actually 2.71828, right? Like that. So it's an irrational number, right? Okay. So ln, or the natural logarithm, or the ln, is actually the logarithm to the base of e, right? To the base of 2.71828 dot, right? Okay. So using the logarithmic property, so we can combine this using the logarithm laws. So we have ln of nt over n naught. All right. Okay, so this is going to equal to, of course, t minus 0 is just t. So we have negative lambda t, right? So we can raise e to the both side. So e. So this e, which is the Euler's number, which its value is actually 2.71828 dot. So this cancels out with this, so we just have nt over n naught equal to e to the negative lambda t, right? To the negative lambda t. Okay. So we have, so this is the integrated decay equation, right? This is the decay equation. So we could still write it in this form, nt equal to, so if we should multiply both sides by n naught, so we just have n naught e to the negative lambda t, right? So where n naught is actually the amount that you start up with, lambda is actually the decay constant, and this is the time it takes for n naught to reduce to nt, right? So this is the decay equation. Okay, this is the decay equation. So let's actually use this to derive the formula for half-life. Of course, we know that in previous videos, we see the relationship between half-life, the disintegration constant, and the fraction that remains, the fraction that decayed. So we talked about that in the last videos, and we solved examples on that. All right. So we say that t, which is the half-life, is actually equal to t small t over number of half-lives, right? Okay. So let's derive that. So let's derive that using this equation here. Of course, we do know that the half-life is actually the time it takes for n naught to reduce to n naught over 2, right? Okay, because it's the time taken for a sample of a radioactive material to reduce to half of its initial amount, right? So we start up with n naught, which is equal to this, and we end in nt, right, which is equal to this, right? Okay, so let's input those values here. So nt is going to equal to n naught over 2, right? Because that is the final value, half of its initial. So nt here is going to be equal to n naught over 2 equal to n naught, right? So what is n naught? N naught is actually n naught. So we have e to the negative lambda. Of course, t in this case is actually the half-life, right? It's actually the half-life. Okay. So this is going to cancel out with this, and we just have 1 over 2 on the left hand side, and that is equal to e to the negative lambda capital T. So let's find the natural logarithm of both sides. So we have ln 1 over 2 or ln 1 over 2 equal to, so if you should ln this side, so if you should find the natural logarithm of this side, of course it cancels out. So if you have natural logarithm of e to the negative capital T, negative lambda capital T, that is just equal to negative lambda T. So we have negative lambda T right over here, right? So using logarithmic law, this is still the same thing. So ln 1 over 2 is still the same thing as negative ln 2, right? Using logarithmic law. So this is equal to negative lambda capital T. So this cancels out with this. So we see that the half-life, which is capital T, is equal to ln2 over the decay constant. And if you should press the calculator, ln2 is actually 0.693 over lambda. Remember, the unit of lambda is actually per seconds, which corresponds to hertz, right? Okay. But in radioactivity, we like to use what? Per seconds. Okay. So we have actually derived the equation for half-life. Right? That's the equation for half-life. So let's solve some example using this equation. Okay, let me change color. Okay, so we example 1. So we a piece of radioactive material contains 10 to the 20 atoms, right? 10 to the 20 atoms. So it contains 10 to the 20 atoms. So n is what? 10 to the 20 atoms. All right. So if the half-life of the material is 20 seconds, the number of disintegration in the first seconds is, all right, so the number, so we actually find the number of disintegration in the first seconds. So what does this actually mean, the number of disintegration in the first seconds? Of course, that is just the n over the t, right? Number of disintegration in the first seconds, right? So we have to find this. Of course, we know that it is equal to negative lambda t, right? Negative lambda t. Okay, negative lambda t. So we're actually given the half-life, right? 20 seconds. So we could let this equal to what? Capital T, right? Capital T. Sorry, this is supposed to be n, right? This is n. So this is actually n, which is a number that we start off with, right? And this is lambda, right? Okay. So we know the number that we start off with, and we know the half-life. So of course, if we know the decay constant, then we can find the number of disintegration for the first seconds, right? Number of disintegration in the first seconds. And we do know that lambda is going to equal to what? 0.693. 693 over capital T, right? So lambda is going to equal to 0.693 over what's capital T? Capital T is actually 20 seconds, right? 20 seconds, and this is, if you press the calculator, you have 0.03465, 0.03465. So from this we can plug in lambda, since we know n to be 10 to the 20th to the 20. So the n over the t, which is negative lambda n, is actually, what is lambda? Of course, we found that to be 0.03465, right? So we multiply that by the number that we start up with, which is 10 to the 20, right? Of course, there is a negative sign there. So the n over the t is equal to, so let's count back. So we have 1, 2, so we have 3.465 negative times 10 to the, so since we count backwards, so we have by 2, so we have 20 minus 2, so we have 18, right? So we have 18. Now we care about the number of disintegration in the first seconds, right? We don't care about the signs. So it is actually equal to approximately 3.47 times 10 to the 18, right? So the answer is A. All right. So the answer is A. So example 2, a radioactive element has a decay constant of 0.077 per second. Calculate its half-life. All right. So decay constant is equal to 0.0077 per seconds. So calculate its half-life. Of course, we know that half-life is equal to 0.693 over lambda, right? So we plug lambda in, so we have 0.693 over, what is lambda? Of course, lambda is actually 0.077, and this is going to equal 9 seconds. 9 seconds. All right. So that is 9 seconds. So example 3. So the half-life of a radioactive substance is 2 seconds. Half-life is 2 seconds. Calculate the decay constant. So calculate the decay constant. Of course, decay constant is going to be equal to 0.693 over capital T, right? So we have 0.693 over, what is capital T? 2 seconds. So we have 0.347 per seconds. Okay, 0.347 per seconds. Now before I do this, you try this. All right, so if you have given me a go ahead. So we have a radioactive element decays to 1/8 of its original quantity in 9 seconds. Calculate its decay constant. Of course, what does this mean? A radioactive element decays to 1/8 of its initial quantity, right? So it reduces from 1, which is 100%, to 1/8, right? To 1/8, right? So this is the original amount, which is the initial amount, m0, to nt, right? So of course we have to calculate what the decay constant. Now we don't know the half-life, right? But we don't know that from the previous video. We know that half-life is equal to of course we're given 9 seconds, right? 9 seconds. 9 seconds is not the half-life, right? 9 seconds here is not the half-life, right? So they say because it reduced to 1/8, not 1/2, right? Or the half, right? Not actually from 1 to the half, right? So 1/8, it reduces to 1/8 of the initial quantity. So t there is 9 seconds. So we know that from the previous video that capital T is equal to small t over number of half-lives, or logarithm to base 2 of r. What is r? What is r? Of course, it is actually the initial over the final, right? Which is actually the disintegration ratio, right? So what's the initial? We have 1. And what's the final? 1/8. So we just have 8, right? So r is equal to 8. Okay, so r is equal to 8. Okay, so capital T is equal to, what is small t? Small t is actually 9 in the question, right? So we have logarithm to base 2 of r. What is r? R is actually 8. And if you notice, 8 is actually 2 to the third power, right? So if you find the logarithm of that, that is just 3, right? So we have 3. So we have 9 over, what is this? This is actually 3. So 9 over 3 is actually 3 seconds, right? So the decay constant is going to be 0.69 over capital T, which is actually 3, right? Which is actually 3, and this is going to equal to 0.231. I've run out of time. See you in the next video.